High availability and fault tolerance both use redundancy and services that implement redundancy to help you achieve the continuous functioning of your architecture, right? But they're implemented in different ways. They have different objectives and, of course, different complexities and different costs, because obviously when something is more complex, it's going to cost you more. But we can summarize this in one line. I'm going to actually use some diagrams to explain the concepts, and then at the end I'll give you the one-line summary. But let's dive in and talk a little bit more about each one of these concepts. With all that being said, hi, I'm GPS. I do cloud things at Microsoft here on YouTube. Don't forget to like and subscribe so I can keep making all this awesome free content. And welcome to a new video. The objective of high availability is to minimize downtime and provide seamless experience to users. It uses an active-passive configuration, less complex, which also means less expensive, okay? And we are not aiming for 100% uptime because that's not achievable with high availability. When we take a look at fault tolerance, we'll talk a little bit more about that. And again, just keep in mind it's minimized downtime, right? So for example, here we have an architecture in the East US 2 region. East US 2 has 3 availability zones, but we're utilizing AZ1 here. And I have pretty much a duplicate of that architecture also in AZ2, but you can see it's grayed out because these are components on standby. And this is what we mean when we talk about an active-passive configuration. We have our active configuration and our passive configuration that kicks in if we were to experience a fault in AZ1. So you see we have a load balancer distributing to our web tier, and then a load balancer distributing to our data tier. So in the case of high availability, what happens? Well, when a fault occurs, we have, again, that architecture, but there's a switch. And now our active configuration becomes what was passive previously. So our AZ2 kicks in and our AZ1 becomes the unhealthy components. Self-healing needs to kick in. Maybe you're using a scale set, it needs to add more instances, whatever the architecture needs to do to put itself in a healthy state again, and then it becomes the passive configuration. And then if you need to do the switch again, then you'll do the switch again. But the key here is within that time where there's a switch, there is going to be downtime, but the objective is to minimize the downtime. So ideally, you architect your components in a way where that downtime, you can achieve 99.0 or 9 or 999, whatever. You can, because you have SLAs to meet with your clients, okay? But that switch is what is the key when it comes to high availability. Okay, so if we switch into fault tolerance, well, what is the objective here? The objective with fault tolerance is to maintain correct functionality in the presence of component failures, right? So it uses an active-active configuration, no longer active-passive, active-active, more complex, which also means more expensive. I also have a diagram here, and we can take a look. We can already see this is a lot more complex. We're utilizing all 3 availability zones available to us in Azure. East US 2, we have AZ1, AZ2, and AZ3, essentially replicated architecture across all of these availability zones. And we have traffic that's being distributed. I probably should have added let me see here. Another load balancer probably would have been somewhere here. So if we move this higher up, probably would have been something here, right? So you have 100% of your traffic being distributed amongst these 3 different availability zones within your region. If for some reason here this would turn into, like if this were to stop working, so we'll just actually use a pencil. Like if this were to stop working, then load balancer would know, okay, now I can distribute the traffic amongst AZ1 and AZ2, and there would be no downtime there because the architecture to take care of that and handle that load is still in place and it still works. So ideally, your architecture deployed in AZ1 could handle 100% while your AZ2 and AZ3 come back up, or maybe AZ2 is down, AZ1 and AZ3 are available. Well, one of your architectures would need to be resilient and redundant enough to take care of that until it kicks back in. Now, let's move actually over here, right? So that's what I'm explaining here.
So error detection picks up the faults, and then the traffic is divided between the available infrastructure, so in this case, AZ1 and AZ2, and then self-healing kicks in to put this availability zone or the infrastructure in here back into a place where it's healthy, and then the load balancer can come and say like, oh, okay, the health checks will tell the load balancer like, oh, this availability zone, the architecture in here is available to now pick up traffic once again. But obviously you can tell like between the complexity just by looking at the diagrams themselves that this compared to this, there's a lot more going on here. Essentially you end up with, well, more than one instances of your architecture that are active. So it's not necessarily that you're paying 3 times as much. It could end up being that, but the fact is it's just going to be more expensive. So keep all that in mind. But now you know the differences between these two.
Okay, so one line summary, so you can really sound like you know what you're talking about, would be highly available systems switch to backup resources when failures occur. Fault-tolerant systems continue functioning without requiring a switch. Keep that in mind. And it makes sense. Like we saw in the diagram, you have an active-passive configuration when it comes to high availability, and when it comes to fault tolerance, you have an active configuration, right? Because there's no switch there. Let me know what other concepts you want us to talk about, clear up, and I hope you learned something, and I'll see you in the next one.